As we continue to look at the motion of a particle in a linear motion, we'll go back to the class 1 and look at the equations that we developed. First of all, by definition, velocity is the time rate of change of position, and acceleration is the time rate of change of velocity. Now, we've shown these kind of as scalar equations rather than vectors, because if we're moving along a straight line, we usually just say a positive is to the right, negative is to the left, so we let the sign take care of the direction. By solving both of those for dt and equating them, we have the equation AdS equals VdV, which we're going to use a little bit later on. We also have a special case when the acceleration is a constant. Then doing these integrations, of course, are very easily, and we come up with closed form equations for velocity and position, as well as this one, the v squared equation that does not use time and just relates velocity to positions for a constant acceleration. So, working some of the problems, here's one where we have the position of a particle given as a function of time. And the question asks, what distance does a particle travel between two time steps? Well, it's pretty easy just to plug in 0 and 8 into the equation for x, and we find those values are 10 and 26 inches. So we might ask ourselves, does it mean that our total travel distance is 16 inches? Well, when you look at that position, notice that there is a negative sign in there. So it is possible that the particle changes direction. And when we plot that up, we can see that that is indeed the case. That in this case, a little over 1 second, this particle goes from moving in the positive x direction, starts moving back negative, and at about 5.5 seconds or so, reverses direction again. So even though the difference between the starting and ending points is 16 inches, we've traveled a lot further than that. So, how do we solve this problem? Well, we need to figure out the time steps at which the particle changes direction and the values of x at those particular points. In other words, local max and min values of x. So as we learned in calculus, if we want to find a local max, local min, we take a derivative and set that equal to 0. And of course, the derivative of x with respect to time, by definition, is the velocity, which makes sense too. If a particle is going to change direction, it has to come to a stop momentarily before changing direction. So wherever we see a velocity equals 0, we know we're at a local max or min. And similarly thing, if you have a variable acceleration, that you can find local max and min values of velocity when the accelerations are equal to 0. Now here's another example problem. In this case, it says we drop a ball from 20 feet. We have to make an assumption here that there's no air resistance, and over 20 feet that would probably be negligible. And how fast is it going just before it hits the ground? Well, for this, we do have a constant acceleration, and that is g. And the values for that are shown here, 32.2 feet per second squared, 9.81 meters per second squared. Those are the ones we'll use mostly in this class. Sometimes, especially in machine design, we use the 386.1 inches per second squared, since we tend to look at motion and say inches per second rather than feet per second. And so if we use y as the position instead of x, since again our motion is going to be in the y direction, and positive y is upward, then of course g is going to be acting downward, and so in the negative y direction. And plugging into our, again, constant acceleration equations, we get these things. So, two ways to solve this problem. One way is to set the y value equal to 0, solve for time, and then plug back into the velocity equation. But the last one is the easiest one to use because of the fact that we're not asked for how long the ball drops, only for the velocity. And so we can relate the velocity to that change in position directly and not have to find the time. Here's one where the acceleration is given as 3s. So s is the position in meters. So we don't have a constant acceleration. We also don't have an acceleration as a function of time. We have acceleration as a function of position, so we want to start with that equation, AdS equals VdV. Just have to integrate both sides. The limits of integration will be from position s equals 0 to position s equals 2 meters, and on the right side because we start at rest, velocity is 0 at s equals 0 to the velocity we're trying to find at s equals 2. And so remember, when you integrate v dv, it's not v, it's 1/2 v squared, and from that you can solve for your value of speed. Now, all these problems, remember that you can always use a numerical solution rather than an analytical solution. So sometimes you come up with an integral that's very difficult to solve, and rather than try to look it up for the solution, you can estimate that with numerical integration. And we work a problem like that in class. Also, if you have an analytical solution that you're not totally 100% sure of, you can do a numerical solution as a quick check for that. So next class, we're going to look at graphical solutions, and just understanding the relationships between position, velocity, and acceleration. I think graphical solutions, looking at those, kind of helps to create that. So we'll be creating graphs that use time as the independent variable and use the slopes and the areas under the curves, in other words the integrals, to solve motion problems similar to the ones we've done analytically so far.